Chapter 8, Part 4. At the end of Part 3, we were looking at how you could visually correlate the units on one side of a canyon with the units on the other side of the canyon by simply looking across and seeing that they were the same units. So what makes correlation different from the other four relative age principles? Well, the other four, original horizontality, superposition, cross-cutting, those are all determining age relationships at a location. Correlation is looking at the rocks at one location and adding a second location in there. So it's determining age relationships between units at two or more locations. Are the rocks at Bentonville the same age as those at Fayetteville? Are the ones at Fayetteville the same age as Fort Smith? Are the ones at Fort Smith the same age as the ones in Denver? Are the ones in Denver the same age as the ones near Moscow? So what we're talking about is being able to look at a sequence here and look at a sequence there and determine which sequence is older or younger. And so we've seen that one of the ways that we can correlate is visually across canyons. As long as you can see the rocks on the other side, there's not much of a problem. But you can't stand in Bentonville and see the rocks in Fayetteville. You certainly can't stand in Denver and see the rocks in Moscow. So visual correlation only gets you so far and can actually be really misleading. The Navajo sandstone and the Coconino sandstone are two sandstones from the Utah, Arizona area out west that look extremely similar. They're a white, hard sandstone. And if you were to visit the Navajo sandstone at Zion National Park and then travel in your car to the Grand Canyon, you might say, oh, there's that rock unit again. You might try to correlate those as saying they're the same age because they look so similar. They both form a cap rock in those places. However, when you zoom out and look at the whole region of southern Utah and northern Arizona, we see that actually the Zion is much higher up in the section than the Coconino is. So the Zion is actually much younger than the Coconino. We could drill into the area of the Navajo sandstone and, did I say sandstone? Of the Navajo sandstone and eventually reach with our drill bit the Coconino well below that. So in this case, correlation, visual correlation kind of lets us down. So ultimately, in order to correlate correctly, you ultimately need to be using fossils. So what is a fossil? Fossil is a remain of an organism. It's usually part of an exoskeleton that has either been preserved or has been replaced by another mineral, but it is a remain of an organism. And one thing that we know that organisms do over time is that they adapt to external pressures and evolve. They adapt to, well, I don't want to say survival of the fittest, it's more accurate to say natural selection, and the ones that can adapt better to the external pressures wind up having more offspring. So those with that mutation or adaptation ultimately replace the ones without it over time. For example, the horse. The original horse looks nothing like today's horse. It was about the size of a poodle. And not one of those big poodles either, the type of small poodle you think of. And it had toes. But over time, it evolved into the giant animal we see today. So if we look at a sequence of rock units, you know, here we got about 9 different rock units in this sequence. And we're looking at an organism that appears to be evolving over time. It started from a straight-shelled organism and becoming a coiled shell organism. So if we say that this is Bentonville here, and if this was Fayetteville here, we could say, oh, well, if I see that organism, that comes from the same time period as this area over in Bentonville. But if we see this one, we would say that comes from the same time period as way up higher there. In other words, this guy's not around anymore. It either disappeared, became extinct, or evolved into these guys. So the presence of certain fossils tells us very much what time period those things were from. And this type of correlation can be done across the globe. It can be done from any two areas that happen to have the same type of widespread index fossils. Not all fossils work well as index fossils, but the ones that do, you can correlate across any distance pretty much and tell the relative age relationships. Now let's throw one more thing in here. What if inside of this sequence, what if instead of excuse me, instead of this organism here, what if this was a lava flow? So the rest of these are sedimentary units, but here we have a lava flow. So you had lava that flowed on top of this sedimentary unit, and then later on it was buried underneath the ocean and more units were deposited on top of that. If you have a lava flow, one thing you can do with igneous rocks that you cannot do with sedimentary rocks is that you can date them. Igneous rocks have radioactive isotopes in them that you can date. So think back to your laundry pile again. Remember, your oldest laundry is at the bottom of the pile. Your newest laundry is at the top of the pile. What if partway in that pile you dig in and find a receipt in a pair of pants? Receipts usually have dates on them, don't they? So being able to date a rock then tells us that everything below that is older than that actual age, and everything above that is younger than that actual age. If we have a lava flow here and maybe the occasional lava flow elsewhere, then we can start to bracket these and say, well, this is older than 35 million years. I'm just coming up with a number. Older than 35, but younger than 40. So then, once we get these absolute dates thrown in there here and there, we can start to correlate this all the way across. Uh-oh, I've got my lava sticking with me there, which I really don't want. And because I'm fairly new to VidGrid, I'm not sure how to get rid of it. So I'm going to give me a second to try and figure this out. And I found the eraser tool pretty quickly. So having the occasional lava flow here and there allows us to put actual dates on them. 200 million years, 300 million years, 250 million years. So ultimately, the result of all this is that geologists, by correlating using fossils and the occasional lava flow or igneous intrusion, have been able to set up the geologic time scale across the entire planet. And so the geologic time scale is divided into eons, eras, periods, and epochs. I'm going to hold you responsible for this geologic time scale, but not the whole thing. The important parts to me are these three eras: Paleozoic, Mesozoic, Cenozoic, and the periods that are within each one. These are time periods, and they range from about 10 million years each to sometimes about 65 million years each, 80 million years for the Cretaceous, which is a pretty thick time period. But I want to talk about a few things about the geologic time scale. I don't want you to know any dates on this time scale. I just want you to know the periods and the eras in order. I also want you to notice a change. Look at the tertiary up here. So we'll get the drawing out again. Look at the tertiary. Just a few recent years ago, just a few years ago, we abolished the tertiary period and replaced it with the Paleogene and Neogene period. So if you see the tertiary referred to, that's a little bit obsolete. So it's been divided into the Paleogene and Neogene. By the way, today we sit in the Quaternary period, the recent or Holocene. Some would call it the Anthropocene, but that is a lecture for a different class. Looking at the geologic time scale, we see that most of the time in this scale is actually in the Precambrian. In fact, 4 billion of the 4.5 billion years that the Earth has been around were in the Precambrian period, and I told you not to worry about that part. Why? Mostly because there just wasn't a whole lot going on during the Precambrian. For about the first billion years or so, there was no life. And then for the next 2 billion years, there was life, but it was mostly algae or bacteria. It was a really dull time most of the Earth's history was a pretty dull time as far as life. Around the beginning of the Cambrian period, we have what is called the Cambrian explosion of life, which may or may not have been an actual explosion, but the fossil record appears, it kind of appears that it was in the fossil record. And so then we have Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, Permian, Triassic, Jurassic, Cretaceous, Paleogene, Neogene, and then Quaternary. If you need assistance in memorizing this, you can use any number of mnemonics that will help us remember that. So the new one, so this one up here, camels often sit down carefully, that is, oh no, both of these actually work for Paleogene and Neogene. Cambrian, Ordovician, Silurian, Devonian, Carboniferous. Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, Permian, Triassic, Jurassic, Cretaceous, Paleogene, Neogene, Quaternary, which is modern day. Most of the stuff in this time scale happened well into the past, long, long ago. One way to look at this is that if you had the history of the Earth's entire history from beginning to end as a trip from Los Angeles to New York, then most of that trip would be Precambrian. In other words, really not a lot going on. We would not get to the Cambrian explosion till around Pittsburgh, and we wouldn't even get dinosaurs till we were almost out of Pennsylvania. The dinosaurs, which were around for 200 million years, only have this little stretch of the trip to them. And human recorded history really only goes partway across the street at the very end of our journey. 2,000 years ago is just a sidewalk's width. Human lifetime is a fraction of an inch on there. So we in geology think of time as a little bit different than you may be accustomed to thinking it. It is, I don't want to say infinitely, but it is several orders of magnitude deeper and longer than what you may be used to. It is exponentially larger. Many of the things that we see happened sometime in this timeline, and very few of them happened in the last 100 or the last 2,000 years as far as geologic things are concerned. You may have seen this presented another way, whereas if Earth's history was a day, then everything that humans did comes in the last 3 seconds of that day, of a 24-hour day. But all the geologic stuff happens sometime in those other 24-hour periods. So that is the end of chapter 8. The next chapter that I'm going to be posting will be chapter 1, which is a kind of an introduction to plate tectonics.